Hello students, welcome to the next section of power amplifiers, and today we are going to discuss about class A power amplifiers. Well, it is the most ordinary used model of power amplifier configuration, that is the class A amplifier. We can say it is the simplest form of power amplifier that uses a single switching transistor in CE common emitter configuration that produces an inverted output. The transistor is constantly biased on. Due to this biasing, the circuit conducts during one complete cycle of the input signal and produces minimum distortion and maximum amplitude of the output signal. Class A power amplifier output stages can use a single power transistor or pairs of transistors attached to share the high load current. The simple and fixed bias circuit connection is displayed. The circuit is able to handle the large signal circuit in the range of volts. The transistor used in a power transistor that is capable of operating in the range of a few tens of watts. The efficiency of this circuit is very poor, so the circuit is not very good to be used as a large signal amplifier. Now let's talk about the DC bias operation. The DC bias is set by VCC and RB fixes the DC bias current at IB, that is equal to VCC minus 0.7 volt by RB, that is equation 1, with the collector current then being IC, that is equal to beta IB, and this is equation 2. With the current emitter CE voltage, we can say VCE, that is equal to VCC minus ICRC, and this is equation 3. The output collector characteristics in this DC bias configuration is displayed. An AC load line is drawn using the values of VCC and RC. The intersection of the DC bias value of IB with the DC load line then determines the operating point, that is also known as Q point. Now let's talk about the AC operation. When an input AC signal is applied to the amplifier, the output will vary from its DC bias operating voltage and current. A small signal input will cause the base current to vary above the below the bias DC point. As the input circuit is made larger, the output will vary further around the established DC bias point until or either of the current or voltage reaches a limiting condition. Power considerations. The power into an amplifier is provided by the supply with no input signal. The DC current drawn is the collector biased current ICQ. The power drawn from the supply is Pi of DC, that is equal to VCC of ICQ, and this is equation 4. Even with an AC signal applied, the average current drawn from the supply remains the same. The equation represents the input power supplied to the Class A series fed amplifier. So the output power can be calculated as, using RMS signals, the AC power delivered to the load RC can be expressed using PO of AC, that is equal to VCE of RMS multiplied by IC RMS, and this is equation 5. PO0 of AC, that is equal to IC square RMS multiplied by RC, and PO of AC is equal to VC square RMS by RC. Using peak signals, the AC power delivered to the load may be expressed using PO of AC is equal to VCE of P multiplied by ICP by 2. Further, PO of AC is equal to IC square of P multiplied by RC by 2. And then PO of AC is equal to VCE square by 2RC. Using the peak to peak signals, the AC power delivered to the load may be expressed using P naught AC, that is equal to VCE P minus P and IC P minus P by 8. And after further simplification, we get the equation as P naught AC, that is equal to Vc square of P minus P by 8 Rc. Now the efficiency. The efficiency of an amplifier represents the amount of an AC power delivered from the DC source. The efficiency of the amplifier is calculated using percentage eta is equal to P naught AC by Pi DC multiplied by 100%. For Class A amplifier, the maximum efficiency can be determined using the maximum voltage and current swings. For the voltage swing, it is maximum VCE of P minus P is equal to VCC. For the current swing, it is maximum of IC P minus P, that is equal to VCC by RC. Using the maximum voltage swing in the equation 13, we get maximum P naught AC, that is equal to VCC of VCC by RC by 8. And maximum P naught AC is equal to VCC square by 8 RC. The maximum power input can be calculated using the DC bias current set to 1/2 of the maximum value. So the maximum PI of DC, that is equal to VCC of maximum IC, is equal to VCC by RC by 2. And after further simplification, we get maximum PI of DC is equal to VCC square by 2 RC. Again, we can use equation 14 to calculate the maximum efficiency. So the percentage eta efficiency is equal to maximum P naught AC by maximum Pi DC multiplied by 100%. So putting the values in the equation, we get the efficiency is 25%. Thus, the maximum efficiency of Class A amplifier is 25%. With this, we have come to an end of this lecture about Class A power amplifiers. And today we have learned Introduction to Class A amplifiers, DC operation of the amplifier, AC operation, power considerations, output power derivation, and efficiency calculation. We will meet again with another interesting topic of power amplifiers soon. Till then, keep watching and keep learning. Bye.